Welcome to Compound Insights, a podcast by CFA Society New York. I'm your host, Rob Rowan. Today we're talking about a very interesting way to compare different risk forecasts, and we're going to go deep into some statistics. This will be a very sophisticated discussion, so right now I'm giving you all a chance to get off the treadmill, put down the dirty dishes, or stop doing whatever else you do while you listen to podcasts. This one is going to require some focus. Our expert today is Jose Minchero of Bloomberg, where he is head of portfolio analytics research. Previously had quant roles at MSCI and Thomson Financial, and he taught physics at University of Rio de Janeiro. He got his BA from University of Colorado and his PhD at Cal Berkeley, and he is a CFA charter holder. Jose, thank you for being here with us today.
Thank you very much, Rob. It's a pleasure to be here.
Okay, so could you please begin by giving us a briefing on the Q statistics that you used in your research and explain why you think it works better than other measures that some of the CFA New York members might be more familiar with?
Yes, that's a great question. Thank you very much. Well, we've been developing these factor risk models for many, many years. And let me begin by saying that they're used for two basic purposes in the industry today. The first use case, which is probably the leading use case, is to make volatility forecasts of portfolios.
Hmm.
And of course, in that case, what you would like is a set of accurate risk forecasts. And the second major use case is mean variance optimization, which
Right.
is the portfolio construction technique pioneered by Harry Markowitz. So in the first case, we really need to ask ourselves, how how can we have confidence that the risk model that we're constructing actually works? And if we're gonna make another risk modeling decision, how can we be confident that this risk modeling decision actually improves the quality of the risk model? So that's the question we've been thinking about for many years. And to get to the first half of that question, which is how can you be confident that a risk model is providing more accurate risk forecasts than, let's say, another risk model, you need some statistics that's going to help analyze that. Now, the leading statistic that has been used for many years is the so-called bias statistic. The bias statistic essentially represents the ratio of realized risk to predicted risk. So what you would like is a bias statistic that is close to one. And the way that the bias statistic is computed is by using the risk model to predict the volatility of a portfolio at the beginning of some period of time. And then you observe the return of that portfolio over some forward-looking window. And then by dividing the portfolio return by the beginning of period volatility forecast, you essentially convert the portfolio return into a z-score. And if your risk forecasts are correct, the standard deviation of those z-scores, which is the bias stat, will be close to one, or in expectation, it would be equal to one. Now, the bias stat is a great measure, and we use it extensively, but the shortcoming of the bias statistic is that it is susceptible to error cancellation.
Yes, which is actually part of level two, I think, CFA level two. Yeah,
Oh,
yeah,
awesome.
it may have been changed since you took it, but this is something that many of the CFA members are kind of familiar with. So
Oh,
please continue.
that,
I just thought I'd take
yeah.
that walk down memory lane for everyone.
Oh, yeah. That's great to know. CFA is a great program. So yeah, let's say you're looking at the bias stat of a portfolio over a 10-year period. If you over forecast for 5 years and under forecast for the next five, over 10 years, maybe your bias stat's equal to one, does not mean you had accurate risk forecast. So the better measure is the so-called Q statistic. So without getting into too much detail here, the Q statistic is also a function of the z-scores, but instead of taking the standard deviation of the z-scores, it's basically every single observation has a Q statistic associated with it. And then by averaging these Q statistics over a large number of portfolios over a long period of time, you can determine with a high statistical confidence that one set of risk forecasts was more accurate than the other. Now, the Q statistic has one crucial property, which is that it is minimized in expectation when you use the true volatility to make every single forecast. So there's no possibility for error cancellation in the Q statistic. If you over forecast some observations, under forecast others, both of those errors are going to lead to expected increases in the value of the Q statistic. So the Q statistic is something that we use very extensively in back testing our models.
Okay. And what do you think is the sort of minimum time frame you can do that over? Because it sounds like that's also important in this.
Yeah, so it's the minimum time frame as well as the number of portfolios that you're looking at.
Sure.
Um,
Yeah. That's
yeah, so
the other metric,
yeah,
if you will. Yeah.
yeah, so I would say that's a great question. The rule of thumb that we use is that a material difference in the Q statistic is about 0.02. So you have to basically look at how many observations do you need to have a sampling error in the Q statistic that is less than 0.02.
Right.
And I don't know the exact number for that, but I would say it's going to be in the order of several thousand observations. Could be in the hundreds, but it's somewhere in that vicinity. So that's why when we backtest our models, we literally have, maybe 1,000 portfolios over 5,000 days. So we have about 5 million observations. So the sampling error is very
Yes,
small there.
that's got
But
to make it by a mile. Yeah. So, yeah. Okay. So would you also, because I think this is an exceptionally important concept to understand in about what you're going to say here, is this concept of term structure of risk.
exactly.
Could you dig into that a little bit, please?
Yeah, so the term structure of risk is something that we've incorporated into our latest generation of models, and it's very important to be cognizant of the fact that when you're making a risk forecast, you have to say over what horizon do you expect that, over what horizon are you making the risk forecast? It's very different to make a 1 day risk forecast than to make a 3 month risk forecast. And just to give you an example, if you take an off-the-shelf index, like say the Russell 1000 index, and you calculate the daily returns, and you take the standard deviation of that, that's going to give you the volatility of daily returns, and then you annualize it by multiplying by, say, the square root of 252 trading days per year, over the last 20 years or so, that volatility would be close to 20%. Okay, so it's fairly high. Now, if you go through the same exercise and you look at now quarterly returns to the Russell 1000, and then you take the standard deviation of those, and then you annualize those by multiplying by the square root of 4 quarters per year, you're going to get a number that's about 16%. So significantly lower. So that's a sign that the U.S. stock market tends to have a negative serial correlation, which means an up return 1 day is more likely to be followed by a down return the next day. So over a longer horizon, those up and down moves tend to cancel out, and they sort of dampen the volatility at longer horizons. So that's what we mean by term structure of risk. Now, if you go to a global model, it's very different, because now with the global model, you have asynchronicity in trading. So an up move in the US is likely to be followed by an up move in Asia the next calendar day. So if you now take the daily standard deviation of global equity returns and you annualize them, what you'll find is that over a quarter, it's riskier than the annualized volatility of daily returns. Okay, because of the asynchronicity of trading. So this is that's just one example, but every single factor in our model is going to have a certain serial correlation. It's important to take those into account when you're making your risk forecast. The second thing that I would point out is when you're testing your risk model to see how accurate are my risk forecast, you have to aggregate the portfolio returns over that particular horizon. So getting back to the example of the US stock market, if I want to say how accurate are my volatility forecast of my quarterly risk model, it doesn't make any sense to look at the daily returns and use that in the numerator if your denominator is a quarterly volatility forecast. You have to make sure that the numerator is synchronized with the denominator. So when you're testing the accuracy of the risk forecast, it's also very important to take into account the term structure of risk.
Okay. What do you think are the main sort of problem or problems in measuring the efficiency of optimized portfolios? I mean, it sounds like we're, getting there. So what do you think? What do you think of the issues, basically?
Yeah, so basically when people do portfolio optimization, the reason that they're doing it is to increase the risk-adjusted performance of their portfolio, right? That's the whole Markowitz theory of portfolio optimization. And the way that many people will actually test this, so suppose that they have an alpha signal, which represents their proprietary view of the expected return of a group of stocks. And they're trying to form a maximum information ratio portfolio using two different risk models, A and B. So what many people will do is they'll use risk model A, form their optimal portfolio using one risk model, and then they'll take the same alpha signal, run it through risk model B, form a different optimal portfolio. And then, of course, they're going to say which risk model delivers a higher efficiency portfolio, and the way that they will often measure this is by looking at the realized information ratio over a period of time. So risk model A gives me a realized information ratio of 0.5, risk model B gives me an information ratio of 0.45. Therefore, risk model A is better than risk model B for portfolio optimization.
Yeah.
Completely the right intuition. However, we argue this is not a good way of testing the efficiency of optimized portfolios.
Right.
And the reason why is because the sampling error in these information ratios is so large. We show this in one of our most recent papers, which was published earlier this year. The sampling error is so large that it's really not much better than flipping a coin to see which risk model produced actually a more efficient portfolio. And what we show is that if you really want to have a high level of confidence, say 99% confidence that risk model A gives you a more efficient portfolio than risk model B, you will typically have to wait decades or even centuries to get to that level of confidence.
Yes.
Okay? Yeah.
Right.
And
That's fascinating.
that's clearly a problem. Now,
yeah.
the better way of testing the efficiency of optimized portfolios, in our view, is to say, let's form a minimum volatility portfolio using two different risk models that has the same exposure to a target factor. And therefore, those two portfolios have the same expected return ex ante. What is going to differentiate those two portfolios is the realized volatility of those portfolios. Whichever risk model does a better job delivering lower out of sample volatility is the better risk model for portfolio optimization purposes. So this is what we call the volatility test as opposed to the information ratio test. And we show in our paper that the volatility test is much more efficient at determining which risk model actually delivers higher information ratio. And we show that typically within a matter of several weeks, you're able to get to this 99% certainty by looking at the realized volatilities of optimized portfolios, as opposed to trying to look at the realized information ratios of optimized portfolios.
Right.
So it's a very interesting effect.
Yeah. That is also fascinating. So, if we could sort of put the two parts together now, how does the term structure of risk reflect the optimized portfolios? How does that?
Oh, yeah, that is a really great question. So in our paper, we looked at constructing portfolios using risk models that were calibrated to different prediction horizons. So let's say you have a daily, weekly, and a monthly risk model. And then so now you're going to have three different portfolios. And what we did in the paper is we said, let's form the minimum volatility fully invested portfolio.
Right.
Okay.
Right.
So like I said earlier, if you look at the US market, the volatility of daily returns is close to 20%. However, if you use a risk model to construct the minimum volatility portfolio, you can achieve a volatility of less than 9%.
Right.
So it's
a huge difference, right? Yeah, it's enormous. Yeah.
Absolutely huge difference. So now, if you were to use a monthly model to form the min vol portfolio and look at the realized volatility over a daily level, it's going to be like 10.2%, which is about 15 or 20% higher than what you get in a daily model. So this shows that the daily model actually does a better job producing lower out of sample volatility over a 1-day horizon. But if you look at the portfolio returns over a 1-month horizon, then it flips. The monthly model produces the lowest volatility of monthly returns, and the daily model produces a higher volatility. Okay,
Right.
so
Right.
this shows that the term structure of risk is very important when creating optimal portfolios. And the other thing that we did in this paper is we said, what is going on? There's some difference in the portfolio composition that's leading to these kind of effects. And
Mm.
what we found, if you think about it, to a first approximation, the min-vol fully invested portfolio can be formed by taking a long position in the market factor, which is essentially the market portfolio, and then hedging the market risk by taking a short position in a beta pure factor portfolio. So that's going to basically tilt your portfolio towards low beta stocks. Now, what we find is that because there is a term structure of correlations, we see that the correlation between the beta factor and the market factor is significantly stronger at the daily level than at the monthly level. And the daily model is going to pick that up. And therefore, it's going to have a more aggressive short position in the beta factor, which is a more effective hedge at a weekly level. But in the monthly model is not going to pick it up because it's calibrated to a monthly horizon. So when we actually look at the composition of the portfolio, we see the portfolio constructed using the daily model has a more aggressive short position in the beta factor than the monthly model. And that is effective at hedging short-term risk, whereas the monthly model is more effective at hedging long-term risk.
Right. This is, I don't want to just want to circle back for a second. The term structure is exceptionally important. Your paper shows this in no uncertain terms, but I don't want to leave one thing on the table before we go, and
Yeah.
that is you also did some work on something else everybody does in addition to Z-quarters regression, and you
Right.
studied regression weighting in the risk model. So what did you find out there?
This is a subject that has not received a lot of attention for many years. But of course, whenever you're building a risk model, you have to estimate factor returns. Whenever you estimate factor returns, you have to use a set of regression weights. And the industry standard for several decades has been to use square root of market cap as the regression weights. However, we know from econometrics that the optimal regression weights are inversely proportional to the specific variance of stocks. So in our latest generation of risk models, we use a close proxy to inverse specific variance, which we call inverse residual variance.
Yep.
And we say there's a couple of very significant benefits to using the more efficient regression weighting scheme. So first of all, this is a fascinating result that very few practitioners are aware of, but you can show mathematically that the pure factor portfolios and the pure idiosyncratic portfolios that come out of your cross-sectional regression, these are the portfolios that give you the official factor and idiosyncratic returns of the risk model. These factor and idio returns are uncorrelated only if you use inverse specific variance as the regression weights.
Right. Right. That's a very important part of it. Only if, yes, yeah,
Only if.
yeah.
And every user of a risk model understands factor returns and idiosyncratic returns are uncorrelated. Everybody knows that. But what few people know is that they're only uncorrelated in theory if you use inverse specific variance as the regression weights. So what we do is like I said, we use a close proxy to inverse specific variance, and we find there's two huge benefits to that. First of all, when you're forming these optimal portfolios that are tilting on individual style factors, we find that in a global model, we obtain about a 10% increase in the efficiency of the portfolio. So, and what that means is that by simply using a more efficient set of regression weights, we're able to increase the expected risk-adjusted performance of these portfolios by about 10%, which is very significant. That's one benefit. And the last benefit that I'll mention is that if you take these portfolios and you decompose them each day into a factor return contribution and an idiosyncratic return contribution, we all know that these two contributions should be uncorrelated. However, if you build these portfolios using the risk model that uses square root of market cap as the regression weights, you find that the factor and idio return contributions are strongly negatively correlated. How strong are we talking about? Typically, the correlations are larger than negative 50%.
Right.
So it's
Negative
a
50%, folks.
ne
That's
ne
yeah.
negative 50%.
Right.
And by using the inverse residual variance weights that we use in our model, we're able to reduce that correlation to essentially zero. So if you look at the average correlation across all of these different factors, I think in our paper it was like 0.01 or something in that neighborhood.
Yeah, yeah, skimming zero for sure. Well, I would like to leave it there, Jose, because you certainly give us a lot to think about and gave a lot of things to the members to think about. So you can find some of Jose's papers just by simply Googling them. You can also find Jose by going on to your Bloomberg and sending him a message. If you have any questions about this, and Jose, I really appreciate you taking the time out to talk a little bit about some of these things that people learn during their CFA exams
Right,
and after that.
right. Thank you very much, Rob. It was a pleasure.